The Module 3 test review. So in the first problem set, we're going to do these. So find a counterexample to show that each conjecture is false. So I already know it's false. So I'm looking for two angles that could be complementary, but they don't have to share a common side. We don't want that to be true. That's how the counterexample works. So if angle A was 30 degrees and angle B was, oops, I drew that badly. But if angle B was 60 degrees, there you go, they're complementary, but they don't share a common side. That would be my counterexample. How about a ray intersects a segment at its midpoint? So that has to happen, but it doesn't have to be perpendicular to the segment. So remember, perpendicular means that it makes a right angle when it hits that segment. So if we have a segment, and I know this is the midpoint because of how it's ticked, it is true that if I drew a ray just right at it, that ray would make a right angle, but the ray could intersect this at any angle whatsoever. So suppose we had a ray here that did that. That is not perpendicular to the brown segment that was already drawn. Okay, in the next problem set, we're doing 18, 19, 24, and 26. We're going to write a conjecture that describes the pattern and then find the next item in the sequence. Well, the first number is 1 times 1, the second number is 2 times 2, the third number is 3 times 3, 4 times 4. So the next number in the sequence would be 25, what we get when we square 5. And the pattern is we're just listing the perfect squares. So we would just list the next perfect square in that sequence. Okay, and number 19, each of these is actually getting cut in half, but as we go through the pattern, we're multiplying by 1/2. And if you multiply 1/8 by 1/2, we end up with 1/16. Okay, and number 24, it looks like we're just rotate the arrow 90 degrees, and we're rotating in a clockwise direction. So we took the original arrow, we spun it 90 degrees, we spun it 90 degrees again, it was pointing down, we'll spin it 90 degrees again, and it should be pointing back to the left. So we have our arrow like such. That would be the final turn. And then in here, this has 3 sides, this has 4 sides, this has 5 sides. We're just adding a side to each figure. These are polygons because we can count the number of sides. So the next one needs to be a hexagon with 6 sides. All right, in the next problem set, we're doing 3 through 5, 10, 13, 16, and 18. All right, identify the hypothesis and conclusion of each conditional statement. I'm going to circle the hypothesis and underline the conclusion. The hypothesis is the part that comes after the if in the statement. So in this case, it would be 2 angles are supplementary. The conclusion comes after the word then. And so the sum of the measures of the angles is 180. There's our conclusion. So the same exact thing here, the part after the if is 2 lines form right angles. The part after the then, the lines are perpendicular. And that's all we had to do was identify them. In number 5, we want to write this in if-then form. So 16-year-olds are eligible to drive. So what has to happen? You have to be 16 years old. If you are, then you're eligible to drive. So that's our if-then statement. If you are 16 if you are a 16-year-old, let's say, then you are eligible to drive. Let me write with a better pen. That's getting a little hard to see. Okay, in 10 and 13, we want to determine the truth value. If it's false, we want to be sure that we're giving a counter example. So if you take a number and you square it and you get 16 for an answer, then that number has to be 4. That's essentially what that statement is saying. Well, this one is false because there is a number that we can square. If I square -4, that does equal 16, but -4 does not equal 4. There's our counter example. And then the same thing here. If an animal is spotted, then it is a Dalmatian. Well, this is also false because we can think of an animal that is spotted. A cheetah is spotted, but not a Dalmatian. But it's not a Dalmatian. Okay, so I could think of an animal that was spotted that was not a Dalmatian. That's how the counter example is going to work. All right, in number 16, we want to write the converse, inverse, and contrapositive of each conditional statement and then determine whether it's true or false. So the first statement is, if a number is divisible by 4, then it is divisible by 2. The converse is formed by swapping out the hypothesis and the conclusion. We're going to trade places. So number 16, the converse is going to be, if a number is divisible by 2, then the number is divisible by 4. That statement is false, and my counter example could be the number 10. 10 is divisible by 2, but it's not divisible by 4. Let's write the inverse. The inverse is where, when we write the inverse, we negate the hypothesis and conclusion of the original statement. So that's going to be, if a number is not divisible by 4, then it is not divisible by 2. So I could say this is false if I can think of a number that's not divisible by 4 but is divisible by 2. And an example of that number might be 22. This is false because 22 is not divisible by 4, but it is divisible by 2. Remember that the converse and the inverse will always have the same truth value as one another. Those are both. If the converse is false, I already knew the inverse was going to be false. And likewise, my original statement's true, the contrapositive is going to have the same truth value. So when I go to write the contrapositive, and to form the contrapositive, we change everything. We negate and swap out the hypothesis and conclusion. So it will become, if a number is not divisible by 2, then it is not divisible by 4. And think of some numbers that aren't divisible by 2. The numbers that come to mind are odd numbers, like 11. 11's not divisible by 2. Well, it's not divisible by 4 either. So this one is true as well. All right, same thing. All we have to do is identify the hypothesis and conclusion of the statement. I think I just did this backward than I did before, but if I'm underlining the hypothesis, its two angles are adjacent, and the conclusion is going to be they have a common side. Notice I'm not including the word if or the word then. It's what comes after the if and after the then. All right, write a 2-column proof. However, we're only doing number 7, and then we're doing all of our properties. So let's do the proof for number 7. We have statements and reasons, starting with my given statement. Statement number 1. Segment AB is congruent to segment CD. We know that because it's given. We want to show that something is equal in the end, so we need to get rid of these congruent symbols. So let's go ahead and say that the distance from A to B is equal to the distance from C to D. That's the definition of congruence anytime we go back and forth between those two statements. Now, I know that AB is 4x minus 6, and I know that CD is 22. I replaced those with their equivalent values. That is substitution. Now let's bring the 6 over. So it will become 4x equals 28. I added 6 to both sides. Since I did it to both sides, that's the addition property of equality. And then we can finish this up, dividing both sides by 4, and we end up with x equals 7. We use the division property of equality to make that happen. And that's what we were trying to prove, so I know I'm finished. All right, let's state properties. So generally speaking, you're asking yourself what changed. What changed when I went from here to here? On the left side, the plus 10 is gone. We got rid of that by subtracting 10. If you do it to one side, you do it to the other. So that was the subtraction property of equality. Same thing in number 10. What changed? It's no longer x divided by 3, it's just x. It's no longer negative 15, it's negative 45. So we multiplied both sides of that equation by 3 in order to make that happen, multiplication. What's changing here? It looks like on the left side of the equal sign, the minus 5 is gone over here. So if you add 5 to this side, you have to add 5 to that side, and that produces the 17. So that was the addition property of equality. And then in number 12, the 1/5 that was in front of each of these distances has gone. It's disappeared. So we've multiplied both sides by 5 and 5. We used, once again, the multiplication property of equality. All right, what changed in number 13, going from here to here? The parentheses are gone. We multiplied the 5 through. That's not the multiplication property, though, because we didn't multiply the right side by anything. We simply passed that 5 through. That's the distributive property. If the measure of 1 is 25 and the measure of 2 is 25, then the measure of 1 has to equal the measure of 2. So they both equal the same thing, so they could equal one another. That could be transitive, or you could also think, I'm going to replace this 25 with its equivalent value. Either one, transitive or substitution. Line 15 really works best for transitive, though. We are truly cutting out the thing in the middle. So AB equals BC, that same BC equals CD, so the first equals the last, transitive. But remember, if we say transitive, we can also say substitution. Okay, the thing that's changing here is the parentheses are gone. 3 times x is 3x. And 3 times that minus 2/3, those 3's will cancel out. So that's the distributive property as well. Okay. All right. Just filling in the statements for the proof. So we've been told that we have some congruent segments here. LK is congruent to NM, and segment KJ, which is this part, is congruent to MJ. And in the end, we want to prove that segment LJ is congruent in length to NJ. Okay, the two sides of that triangle. So we've done something really similar to this in class together. It's done for us, we just need to put the reasoning in. So it starts off by listing the given, and if the next thing we're going to say is definition of congruent segments, then we'll drop the segment markings and just say that these things are equal to each other. That's what it means to be congruent. They're going to have equal distances. Then notice that, so they kind of did a couple of things in this step. This is maybe a little hard to see. They took this original statement, so there it was, LK was equal to NM. They added KJ on the left and MJ on the right. But because those things were equal to one another, that was the addition property of equality. They added equivalent values to both sides. So the addition property. And then they want us to come up with a segment addition postulate. Let me think about which one we should use here. LJ equals MJ. Okay, we're going to do both of those. Here we go. So this first segment over here, this one, I can write that as NM, the small piece, NM, plus the bigger piece, MJ, is equal to the whole thing, JN. And then we can do the same thing on this other side. The small little piece, which is LK, so and the bigger piece, KJ, is going to add up to that whole side, which is LJ. So notice that now that we've written that, we have gone just to saying that LJ is equal to NJ. LJ and NJ show up here and there. I just wrote that one in a different order. And then notice that this statement, the NM plus MJ is here, and the other statement, that LK plus KJ, is there. And we knew that those were equal to each other. So these are equal to one, these are equal, so that means that these two things must be equal to one another. You can say transitive there, we're cutting out the equal things in the middle. And then we're going from our equal statement to our congruent statements. And anytime we do that, remember this one goes both ways. Definition of congruence. You can start with equal distances and end with congruence, or vice versa. It was a biconditional statement. All right, one more proof. Should be easier for us. So we're starting with the given statement. The first thing that happened was the 6 was passed through the parentheses to produce the statement below, distributive, and then 24 was added to both sides, the addition property of equality to produce this, and then we divided both sides by 6, the division property of equality, in order to produce that last statement. All right, finding the measure of each angle. This is just, actually ties to Module 2 a little bit. If this is 90, 5 has to be 90 because they make a linear pair. 7 and 53 are vertical angles, so 7 also has to be 53. And then 6 and 53 form a linear pair. There's 180 degrees there. So if you subtract 53 from 180, that's going to leave us with 127 degrees for 60. All right, we want to find the following. Name a plane that is parallel to ZWX. So ZWX is the top of this box, and the bottom of the box would be parallel to that. Pick any 3 of the 4 letters down here. So the vertices at the bottom are T, U, V, and S. So I'll just call it plane TUV. You could name it differently as long as you name the bottom. Name a segment that's skew to TS that contains point W. Well, remember, skew means that it is not parallel to TS, but it never touches TS. So the segment that contains W that does this one would be this edge of the box back there, segment WU. And then we want to name all segments that run parallel to SV. So segment SV is down here. This is running parallel, that's segment TU, as well as the two edges up top that run in the same direction. So we have segment YX and segment ZW. All right, and then we want to find the measures of these numbered angles here. So number 55, these two angles form a linear pair. They're going to add up to 180. So if we add these two angles together, 2x and 2x is 4x. The minus 4 and the plus 4 will cancel out. The sum of those two angles, so the measure of angle 9 plus the measure of angle 10 equals 180. They make a linear pair. Divide both sides by 4 and you get 45. So if we want to go back and find the measures, 9 is equal to 2 times 45 minus 4, or 90 minus 4, which will give us 86 degrees. And 10 is simply equal to 2 times 45 plus 4. So that'll be 90 plus 4, or 94 degrees. So the measure of 10 is 94, the measure of 9 is 86. The same exact thing is true here. 11 and 12 make a linear pair. So if you add their measures together, that's going to equal 180. 4x and 2x is 6x minus 6. That's what you get when you add those together. That equals 180. Add 6 and 6x equals 186. Divide both sides by 6 and we're going to get 31. So x is equal to 4 times 31, or 124 degrees, and 12 is equal to 2 times 31 minus 6, or that'll be 62 minus 6, which leaves us with 56 degrees. All right, 57 is identical. So add these angles together, it will have 40x plus 100. 40x plus 100 equals 180. Subtract the 100, it equals 80. Divide by 40, and x is 2. So it's just going to be 100 plus 20 times 2. 100 plus 40 is 140. And then down here, it's just 20 times 2, or 40 degrees. Okay, we're doing 8 through 10 and 24, doing all of these problems. Notice these are parallel to each other. So the first thing I'd like you to notice is that y and x are alternate interior angles. So these are alternate interior angles, and those are going to be congruent to each other. However, 55 and x make a linear pair. These have to add up to 180. So if I do 180 minus 55, we're going to end up with 125 degrees for x. And if x is 125, so is y, because the alternate interior angles are congruent to each other. In number 9, these are running parallel. We're looking for the value of the variables here. These angles are alternate exterior angles. So remember, that's the interior. Those are on opposite sides of the transversal outside the lines. Alternate exterior angles are always equal to one another. So we'll set the x minus 10 equal to 104, add 10, and x is equal to 114 degrees. These lines are parallel. The angles that we're looking at are inside the lines. It's a little hard to see where they are, honestly, but the 2x minus 15 is this one, and the x plus 55 is that one. Those are alternate interior angles, and those are congruent. So we'll set the 2x minus 15 equal to the x plus 55. Subtract x from both sides, and you get x minus 15 equals 55. Add 15, and we're going to get that x equals 70. All right, same thing here. We have parallel lines, and we still have to find the value of the variable. Well, 14 and y those are corresponding angles. Corresponding angles are equal to one another, so y is equal to 114 degrees. And then this angle and y make the linear pair. So if I add this angle, which is x plus 12, to this one, which is 114, that should add up to 180. So we have x plus 126 equals 180. Subtract 126 from both sides. That's going to leave us with 154 for x. All right, in number 25, we still have those parallel lines. These two angles are in the same position. They're corresponding. So in order to solve for x, we can set the 3x minus 15 equal to 105. Add 15, and we get that 3x equals 120. Divide by 3, and x is 40. If we plug x back in, 3 times 40 is going to be 120 minus 15, which leaves us, well, I'm sorry, I already knew that was 105 degrees, didn't I? 105. And then these form a linear pair. So if I add the 105 plus this angle, y plus 25, that has to equal 180. Add those together, 130 plus y equals 180. Subtract 130 from both sides, and y is going to be 50 there. And then finally here, so parallel lines, 54 is an alternate exterior angle with this one up here. So this is 54. And that angle makes a linear pair with the 2x. These two are supplementary together. So let's add those together. 2x plus the 54 has to equal 180. Subtract 54 from both sides, and we're going to end up with 126. Divide by 2, and we'll get 63 for x there. And then finally, we finish on kind of a light note. If the measure of angle 2 is 70, we want to find the measure of everything else. Well, 6 is going to be 70 because it corresponds. We've got parallel lines. And then 3 is a vertical angle with that, and 7 is a vertical angle. So 2 was 70, 3 was 70, 6 was 70, and so was 7, but they didn't ask us for 7. All the other angles in this picture will have the same measure. They form a linear pair with 70, so that's going to be 110. So 1 and 4 are 110, 110, and then 5 and 8 are vertical angles, and they're also 110 for the same reason.